Welcome to example number 5. We have a shark that weighs 10,000 newtons that is supported by this cable that is attached to a 4-meter long rod that can pivot about its base. We're asked to calculate the tension in the tie rope right here that is tied between the beam and the wall. And we're also asked to find the horizontal and vertical components of the force at the base of the rod. We're going to neglect the weight of the rod, so we're going to assume that this weight of that rod is weightless or negligible compared to the weight of all of the shark and the tension of the rope and so forth. Okay, so the first thing we're going to do is we're going to draw a free body diagram for this particular body. I'm going to just label the forces right directly on this particular rod that's in equilibrium. So we have the shark that's pulling downwards here. I'm going to label that force as F sub S for a force in the shark, and that's 10,000 newtons. We have the tie rope that is pulling up here. I'm going to label that as F sub T. And then down here at the base of the rod, I'm just going to label two forces that will represent that one single force. This is the vertical component, and this is the horizontal component. I'm just going to label that as F sub Y and over here as F sub X. I don't know the tension, nor do I know these two forces down here in the bottom. So first thing I would probably do is I would actually apply the torque condition because that probably hopefully you might realize that's going to lead you to the fastest way of solving this problem. You could apply the force condition, some of the force in the X, but then you don't know what the tension is in the X direction. You don't know this force. And you apply the force in the Y direction, but you only know this force, and there's also a Y component of that tension, so it's not going to really solve the problem yet. However, if you apply the sum of the torques about some pivot point, that can actually find you a force right off the bat. You see, if you pick this point right here, we'll call that point P, and we do the torques about point P, these two forces, or this one force if you think of it at that base, well, the torque produced by that at that pivot point will be zero because the point of application is at the point, the axis of rotation, and so the position vector is zero, and so there's no torque produced by these two forces. So really we only have two torques to consider if we do it about point P. We have the tension force producing a torque that is going to make the beam move in the direction that is counterclockwise. That will be produced by the tension force. And then the shark will make it go clockwise. So these two torques will add up to zero. So we have the torque produced by the tension, and we have the torque produced by the shark adding up to zero. But the shark, we're going to consider that to be a negative torque because it's clockwise, and the tension, we're going to call that positive torque. So basically these two torques are balancing each other out. So you could write the torque from the tension is equal to the torque of the shark. The torque from the tension is the force of tension multiplied by the distance from the pivot point all the way to here, which is really 4 meters. And then multiplied by the sine of the angle between this vector, r, and this force. Now you can see there's a 60-degree angle here made with respect to the beam and the horizontal, so this angle here is 60 degrees. So therefore the angle between the position vector and the tension is 60 plus 20, which is 80 degrees. And that's equal to the torque that is produced by the shark, which is the force from the shark, which we already know is 10,000 newtons, times the distance r, which is the same thing that we had 4 meters, so it really didn't even actually need the 4 meters, times the sine of the angle between this position vector and this force, so this angle in here. Now if this is 60 and you go all the way down here, that's 90. That means this angle up here is 30 degrees. So it's really the sine of 30 degrees. So we didn't really need to know r, the length of the rod. Actually, it doesn't even matter if it's 4 meters or 10 meters, it would be the same thing, same answer. So we have the force of tension would be equal to the force of the shark, which is 10,000 newtons, times the sine of 30, which is really just a half, and then all divided by the sine of 80 degrees. And that gives you a tension of 5,080 newtons, rounded off to 3 sig figs. So there's part A. Now that we know the tension along here, we know that is 5,080 newtons, we can then find the horizontal and vertical components of the tension. Let's do that. So the x component of that tension, we know this is 20 degrees. We want this side, which is the adjacent side of the hypotenuse, so we're going to be using Ft times cosine of the angle 20 degrees. So that's 5,080, or to be exact, it's 5,077 times cosine of 20. And that gives you a force of 4,771 newtons. Let's find the y component of this tension. So the y component would be Fty will be equal to Ft times the sine of 20 degrees. So it's 5,080 newtons times the sine of 20 degrees. And that gets you a force of 1,736.5 or something like that newtons. Okay, so we need to find out these forces. This is just the x and y components of that tension. We need to find the actual forces at the base. So we're going to now apply the force condition. The sum of the forces in the x-axis should balance out to be 0. So here's our x-axis, by the way. X is to the right, and y is straight up. So the x component of that base force is positive, yet the tension is going to be counterbalancing that, so it's negative. And then there are no other forces that are acting horizontally. So therefore, the horizontal force at the base will be equal just to the tension, the x component of that tension, which is 4,770 newtons, if we round that off. And then if we solve for the y forces, let's continue with our sum of the forces in the y equals 0. And now if we look at the y direction, we have the y component of that tension, which is upwards. We have the shark that is going downwards, and then we're base that is pointing upwards. And so we're solving for Fy. So Fy will be equal to the force of the shark minus the vertical component of that tension. The force of the shark is 10,000 newtons, and the vertical component of that tension, Fty, was 1,736.5 newtons, around there. And that gets you a vertical component of that force of 8,260, we'll just round off to 60 newtons. And that's it for the problem. Now you could continue, by the way, and find the resultant force of Fx and Fy. You'd simply use Pythagorean theorem using these two forces, and you'd end up with a force of 9,540 newtons. And you could get the angle as well by using the arctan of Fy over Fx. And interestingly, that will give you an angle of 60 degrees right along the beam. And that's due to the symmetry of the problem. And that's it for this example.